30 years of staring at the same star system, and astronomers still missed something the size of Jupiter hiding right in front of them. Beta Pictoris is one of the most photographed, most measured, most obsessively studied planetary systems outside our own solar system. It has been a training ground for an entire generation of exoplanet hunters. Every telescope worth mentioning has pointed at it at some point. And yet, in July of 2026, the James Webb Space Telescope looked at that same familiar star and found a giant planet that nobody had ever seen, sitting in the outer reaches of the system, wrapped in a haze of carbon monoxide, water vapor, and methane. Astronomers are calling it Beta Pictoris d, and the way it was found says something bigger than the planet itself. It says that even the objects we think we know best can still be hiding secrets, and that the tools we now have are finally sharp enough to drag those secrets into the light. Let's slow down for a second, because the story of Beta Pictoris is worth understanding before we get to what Webb just did. This star sits roughly 63 light years from Earth, young by stellar standards, only around 20 million years old, which in cosmic terms is practically a newborn. It became famous in the 1980s when astronomers noticed it was surrounded by a huge disk of dust and debris, the leftover material from planet formation, still swirling and settling into shape. That disk turned Beta Pictoris into a kind of natural laboratory. If you want to understand how solar systems are born, you study young disks like this one, because they are essentially frozen snapshots of a process that happened to our own solar system 4.5 billion years ago, long before anyone was around to watch it happen. Over the following decades, astronomers found 2 planets in that system through direct imaging, an incredibly difficult technique that involves blocking out the blinding light of the host star just enough to catch the much fainter glow of a planet nearby. It's the astronomical equivalent of trying to spot a firefly hovering next to a lighthouse from miles away. Those 2 planets, called Beta Pictoris B and C, became minor celebrities in astronomy circles, referenced in textbooks, studied by nearly every major observatory. The system felt, in a sense, complete. 2 planets, a disk, a well-understood story, except it wasn't complete. Webb's instruments picked up something else, something that had been shielded by that same dust and debris that made the system famous in the first place. The disk that helped astronomers discover the first 2 planets was, ironically, hiding a third one. Using its near-infrared spectrograph, Webb detected the chemical fingerprints of an atmosphere out in the colder, dimmer outskirts of the system, well beyond the previously known planets. The presence of carbon monoxide alongside water vapor and methane told researchers they weren't looking at a clump of leftover dust or some optical artifact. They were looking at a genuine planetary atmosphere, one belonging to a giant world with the widest orbit of any planet yet found in that system. Here's why that detection method matters so much. Finding a planet by staring directly at its reflected or emitted light is one thing. Finding a planet by reading the chemical signature baked into starlight passing through or near its atmosphere is a completely different level of detection, and it opens the door to identifying worlds that would otherwise stay invisible forever. Dust disks are notoriously good at hiding things. They scatter light, they create false signals, and they can bury a planet's faint glow under a wash of background noise. Webb's ability to separate a genuine atmospheric signature from all that clutter is what allowed Beta Pictoris d to reveal itself after decades of going unnoticed. Scientists are now describing this technique as a promising new way to track down elusive exoplanets in systems that seemed already fully explored. Think about what that implies. If a system as heavily studied as Beta Pictoris still had a giant planet hiding in plain sight, how many other well-known systems are quietly concealing worlds we haven't found yet? The composition of that atmosphere is not just a curiosity either. Carbon monoxide, water vapor, and methane in specific ratios act almost like a fingerprint of how a planet formed in the first place. Did it form the way Jupiter did, slowly accumulating a rocky core before pulling in a thick blanket of gas? Or did it form through a faster, more chaotic process where a region of the disk collapsed directly under its own gravity? The chemical mixture Webb detected gives researchers clues to answer that question, clues that were completely unavailable before this kind of precision spectroscopy became possible. Every new data point like this refines the model scientists use to explain how planetary systems, including our own, come together out of a swirling cloud of gas and rock. There's an added layer of significance here that's easy to miss if you're not deep in the field. Beta Pictoris d has the widest orbit of the 3 known planets in that system, meaning it formed, or at least now resides, in the coldest and most distant part of the disk, far from the intense heat of the young star. That location matters enormously for figuring out formation history. Planets that form close to their star experience very different conditions, different available materials, and different timescales than planets that form or migrate out toward the frigid outer edges of a system. By comparing the atmospheric chemistry of all 3 planets in the Beta Pictoris system side by side, each one sitting at a different distance from the star, researchers now have something close to a natural experiment, a single system offering multiple data points on how planets forming under different conditions end up with different chemical signatures. That kind of comparison, all three worlds captured by the same instrument using the same methodology, is far more powerful than trying to compare planets scattered across entirely different star systems with their own unique quirks and observational limitations. It's the difference between studying three siblings raised in the same house versus trying to compare three strangers who grew up on opposite sides of the planet. Now, if this were the only unimaginable thing Webb had turned up recently, it would already be a remarkable story. But it isn't. This telescope has been quietly rewriting entire chapters of astrophysics textbooks, one observation at a time, and the deeper you look into what it has found just this year, the stranger and more astonishing the picture becomes. Go back to the earliest days of Webb's science operations, and you'll find one of its most puzzling discoveries, a category of objects nobody had ever seen before, nicknamed little red dots. These are small, extraordinarily compact, and unusually bright objects found scattered across the deep field images Webb captured of the early universe. When they were first spotted, astronomers weren't even sure what they were looking at. Were they compact galaxies packed with young stars? Were they something else entirely? The name stuck because that's exactly what they looked like in the imagery. Tiny, reddish points of light, easy to overlook, yet present in surprising numbers across Webb's deepest exposures. Since that initial discovery, researchers have spent years trying to piece together what these objects actually are, and the picture that's emerging is genuinely strange. Many little red dots appear to be galaxies in an early chaotic stage of assembly, and buried inside a growing number of them, astronomers are finding evidence of actively feeding supermassive black holes. That alone would be an interesting result. But the real jaw-dropping part comes from just how early in cosmic history some of these black holes appear to be growing. One confirmed case, cataloged as Koenig's LRD Z8. 6 involves a supermassive black hole caught in the act of actively growing inside a galaxy, observed at a point just 570 million years after the Big Bang. Sit with that number for a moment. The universe is roughly 13.8 billion years old. 570 million years after its birth is an almost unimaginably early moment, cosmically speaking, equivalent to looking at a human life and finding a fully formed personality within the first few weeks after birth. Supermassive black holes, according to the standard models astronomers have relied on for decades, are supposed to take a long time to grow. They accumulate mass gradually, feeding on gas and merging with other black holes over enormous stretches of cosmic time. Finding one already massive and actively feeding this early in the universe's history challenges the very foundation of those models. This is where the phrase unimaginable really earns its place, because scientists are being forced to consider possibilities that would have sounded like science fiction a decade ago. Maybe black holes in the early universe formed through a process called direct collapse, where an enormous cloud of primordial gas collapses straight into a black hole without ever going through the intermediate step of becoming a star first. That would essentially give these black holes a massive head start, letting them reach supermassive scales far faster than the traditional slow growth model would allow. Webb has already turned up tantalizing evidence pointing toward this kind of direct collapse scenario in other observations, evidence that would have been utterly invisible to any telescope that came before it. The discovery of an actively growing black hole this early, paired with evidence for a formation pathway that skips normal stellar evolution altogether, connects two of the biggest open questions in astrophysics. How do galaxies form, and how do the monstrous black holes at their centers get so big so fast? What makes this even more compelling is that little red dots aren't a one-off anomaly. They're turning up throughout Webb's deep field surveys in significant numbers, suggesting this population of dense, black hole-hosting early galaxies might represent a genuine phase that many galaxies passed through in their infancy, a phase completely hidden from every telescope that existed before Webb's infrared eyes came online. Researchers have even started running simulations, taking galaxies observed closer to our own era and mathematically shifting them backward in time and distance to see whether they would resemble little red dots if viewed at the earlier epoch. The results are helping build a bridge between these mysterious early objects and the more familiar galaxies we see today, suggesting a possible evolutionary pathway. Some little red dots might represent an early, chaotic stage that spiral galaxies like our own Milky Way could have passed through billions of years ago. Before we leave the ancient universe behind, it's worth mentioning that little red dots aren't the only piece of the early galaxy puzzle Webb has been chasing down this year. Researchers have also used Webb to spot something almost the opposite of a fast, chaotic black hole, the ghostly remnant of a star that quietly finished its life without ever announcing itself through visible light. For the first time, astronomers identified a supernova progenitor, a red supergiant star located in a nearby galaxy that had been completely invisible to every other telescope ever pointed in its direction. The star's surroundings turned out to be far dustier than expected. thick enough to swallow its light entirely at visible wavelengths, which is precisely why nothing before Webb had ever caught a glimpse of it. Only by reading the infrared light leaking through that dust could astronomers finally identify the star that would go on to explode. It's a quieter kind of discovery than a hidden planet or an impossibly early black hole, but it carries the same underlying lesson. There is far more sitting behind the dust and distance of the universe than any previous generation of telescopes could ever confirm. Closer to home, within our own galaxy, Webb also helped confirm an entirely new category of stellar object this year, something astronomers are now calling bulge fossil fragments. The prototype example, a dense stellar system called Tarzan 5, sits buried near the crowded center of the Milky Way, an area so thick with stars and dust that studying anything inside it in detail has always been a challenge. By combining fresh observations from Webb with more than a decade of earlier data collected by the Hubble Space Telescope, researchers were able to show that Tarzan 5 experienced not one, but as many as 4 distinct episodes of star formation stretched out over enormous timescales. That pattern rules out the simpler explanation astronomers had assumed for years, that Tarzan 5 was just an ordinary globular cluster, a tightly bound ball of stars that all formed together in a single burst early in the galaxy's history. Instead, it appears to be a surviving fragment of one of the ancient primordial clumps of gas and stars that merged together billions of years ago to build the dense central bulge of the Milky Way. Most of those primordial clumps dissolved into the bulge long ago, blending in and losing their individual identity. Tarzan 5 somehow avoided that fate and survived largely intact, a fossil sitting at the heart of our own galaxy, hiding in a region so obscured by dust that it took Webb's infrared vision working alongside Hubble's long observational record to finally reveal what it actually was. Let's shift gears now, because Webb hasn't just been rewriting the story of the deep, ancient universe. It has also been turning its attention closer to home, and one of its most poetic discoveries this year involves a visitor from somewhere else entirely. In the middle of 2026, an interstellar comet designated 3I Atlas passed through our solar system, and Webb was there to study it. This isn't a comet born in our solar system's Oort cloud or Kuiper belt. It's an object that formed around a different star in a different planetary system sometime in the distant past, and has been drifting through interstellar space for who knows how long before its trajectory happened to carry it close enough for our instruments to examine. Interstellar objects passing through our solar system are exceedingly rare from an observational standpoint. Before this one, astronomers had only confirmed a couple of others, each of which caused a wave of excitement precisely because these objects offer something no local comet ever could: a direct physical sample, observed remotely, of material that formed in an entirely separate star system. Webb pointed its near-infrared spectrograph at 3I Atlas and began breaking down the light reflecting off the comet to determine its composition. What researchers found points toward an origin story stretching back much further than most objects we study. The clues embedded in its chemistry suggest this comet is ancient, potentially older than our own solar system, a frozen time capsule that has been drifting through the emptiness between stars for eons before crossing paths with us. Imagine that for a second. A chunk of ice and rock, assembled around a star we may never identify, ejected from its home system by some gravitational interaction we'll never witness, and then drifting alone through the vast, cold dark of interstellar space for potentially billions of years, only to eventually swing past our own solar system, just as humanity happened to have built an instrument sensitive enough to study it in detail. The odds of that timing alone are worth pausing on. Studying the chemistry of interstellar objects like this gives scientists a way to compare planetary formation processes across completely different star systems. Every solar system that has ever formed represents its own unique combination of the raw ingredients present in that particular stellar nursery: the temperature conditions, the presence or absence of certain elements, the turbulence and structure of the surrounding disk. When an object formed somewhere else finally passes close enough to examine, it's like receiving a message in a bottle from another cosmic shoreline, one written in the language of chemical abundances and isotope ratios rather than words. Webb's ability to read that message with such precision, even on a small, faint, fast-moving target like an interstellar comet, is a testament to just how far observational astronomy has come. A decade ago, an object like this would have been little more than a smudge of light. Now it's a legible record of conditions from a planetary system we will likely never visit and may never even identify. From ancient interstellar wanderers to something happening in real time much closer to home, Webb has also transformed our understanding of weather, actual weather, on planets outside our solar system. This might sound like a strange thing to study given everything else on this list, but it turns out atmospheric behavior on distant worlds tells scientists an enormous amount about what those planets are made of and how they behave. Take the case of a scorching hot Jupiter located nearly 700 light-years away in the constellation Microscopium. Webb observed this planet closely enough to catch something astronomers had never directly witnessed before: a daily cycle of clouds made of vaporized rock, forming and then vanishing again as the planet rotates. Picture that for a moment. Not clouds of water vapor drifting lazily across a blue sky, but clouds condensed from minerals that would normally require furnace-level heat just to turn into gas in the first place, appearing and disappearing on a rhythm tied to this planet's rotation, the same way our clouds shift with Earth's day and night cycle, except built from an entirely different, far more violent chemistry. For 20 years, one of the biggest obstacles in exoplanet atmospheric science has been persistent cloud cover, which researchers have described as something like trying to study a planet through a permanently foggy window. Clouds on these worlds tend to blanket the atmosphere in a way that obscures the deeper layers scientists actually want to study, making it difficult to determine what a planet's atmosphere is truly made of. Watching an entire cloud cycle form and dissipate over the course of a single planetary rotation gives researchers, for the first time, a clear window into the layers beneath those clouds during the moments when the sky, so to speak, actually clears. That's an enormous advance for understanding the true chemical makeup of these worlds, rather than just the composition of the clouds sitting on top of them. Then there's WASP 107b, a planet astronomers have nicknamed a superpuff because of its bizarrely low density, roughly the size of Jupiter, but with only a small fraction of its mass, giving it an atmosphere so extended and loosely bound that Webb was able to detect an enormous cloud of helium physically streaming away from the planet into space. This isn't a subtle process. It's the planet actively losing part of its atmosphere, streaming outward in a visible plume that Webb's instruments were sensitive enough to trace. Watching a planet lose material in real time gives scientists a direct look at atmospheric escape, a process believed to shape the long-term evolution of many planets, potentially even stripping smaller worlds down to bare, rocky cores over billions of years. And then there's a planet with what researchers are calling two completely different twilights, an ultra-hot world where the transition zones between its blazing dayside and frigid nightside behave in strikingly different ways depending on which direction you're looking from as the planet rotates. Twilight on Earth is a brief and fairly uniform transition. On this distant world, Webb found that the physics governing that transition zone shifts dramatically from one side of the planet to the other, revealing atmospheric dynamics far more complex and asymmetric than anything in our own solar system. Alongside all of this, Webb has also found surprising evidence of a thick atmosphere clinging to a small, blisteringly hot rocky planet that scientists previously assumed was far too extreme an environment to retain any gas at all, a discovery that upends assumptions about which planets can and cannot hold on to an atmosphere under intense stellar radiation. Taken together, these atmospheric discoveries paint a picture of a huge diversity of weather and atmospheric behavior scattered across the galaxy, ranging from mineral clouds cycling with the day-night rhythm of a planet, to entire atmospheres physically evaporating into space, to twilight zones that behave like two different planets stitched together at the seams. None of this was accessible before Webb. Earlier telescopes could tell us these planets existed and give rough estimates of their size and mass, but the fine chemical and dynamical detail Webb provides is what turns a distant point of light into an actual world with actual weather, an actual sky, an actual atmosphere in motion. There's one more discovery from this year worth sitting with, because it challenges something so basic about galaxies that it's almost hard to process. Nearly every large galaxy astronomers have ever studied spins. Spiral galaxies, like our own Milky Way, rotate in an orderly, predictable fashion, and even more chaotic, elliptical galaxies typically show at least some rotational motion when examined closely. Rotation is, in a very real sense, part of the basic definition of what a galaxy is supposed to do. Webb, however, examined a giant galaxy and found something astronomers still don't fully know how to explain. It doesn't appear to spin, at least not in any conventional sense. Researchers tracked how material moves within this galaxy and compared it against two others from the same cosmic era, hoping to understand whether this was some kind of measurement error or genuinely represented a different category of galactic behavior. The results held up. This is a galaxy that seems to defy one of the most basic assumptions astronomers have long taken almost for granted. Discoveries like this matter precisely because they're unsettling. Science doesn't advance by confirming what we already expect to find. It advances by encountering results that don't fit the existing framework and forcing that framework to expand or change. A non-rotating giant galaxy sitting alongside galaxies that behave exactly as expected raises pointed questions about how galaxies form, how they evolve, and whether our models have been built on assumptions that only apply to a subset of the galactic population rather than the whole picture. Stepping back from any single discovery, what's remarkable is how all of these findings are connected by a common thread. They were only possible because Webb operates primarily in the infrared, at a level of sensitivity and precision no previous observatory has ever achieved. Infrared light passes through dust clouds that block visible light entirely, which is exactly why Webb could see straight through the dust disk hiding Beta Pictoris d for decades. Infrared light also carries the chemical fingerprints of atoms and molecules, encoded in specific wavelengths absorbed or emitted by different elements, which is how Webb read the atmospheric composition of a comet from another star system, and diagnosed the vaporized rock clouds cycling on a hot Jupiter 700 light-years away. And because the expansion of the universe stretches the light from extremely distant, extremely old galaxies into the infrared portion of the spectrum, Webb's infrared sensitivity is also precisely what allows it to peer back toward the very beginning of cosmic time and catch supermassive black holes in the act of forming when the universe was barely 5% of its current age. This is the telescope's 4th year of science operations, and if this is the pace of discovery after just 4 years, it raises a genuinely exciting question about what the next decade of observations might reveal. Every one of these findings, the hidden giant planet, the impossibly early black hole, the ancient interstellar wanderer, the vanishing rock clouds, the evaporating atmosphere, the galaxy that refuses to spin, represents a small crack in the wall of what scientists thought they understood. And cracks like that tend to spread. Once you find one hidden planet in a system you thought was fully mapped, you start wondering how many other complete planetary systems are hiding something. Once you find one black hole that grew far faster than existing models allow, you start questioning the entire framework for how galaxies and their central black holes co-evolve. Once you find one galaxy that doesn't spin, you start re-examining every other galaxy you thought you understood, just in case there's something you missed. What makes all of this feel less like a series of disconnected headlines and more like a genuine turning point in astronomy is the sheer range of scales involved. In the space of a single year, one instrument produced results spanning from a planet in our galactic backyard to a black hole glimpsed at the dawn of cosmic time, from an ancient wanderer that spent eons drifting between stars to weather patterns unfolding on planets we'll never visit, from a spinning disk of dust concealing a hidden world to a galaxy that seems to break one of the most basic rules galaxies are supposed to follow. No single previous telescope could have delivered that kind of range with this level of detail. That's not incremental progress. That's a fundamentally new capability being applied across the entire breadth of astrophysics simultaneously, and the results are exactly the kind of discoveries that earn the word unimaginable, not as hype, but as an accurate description of results that genuinely sat outside the boundaries of what scientists expected to find. And this is very likely still early. Every one of these discoveries has already sparked new observing proposals, new follow-up studies, new theoretical models, trying to catch up with what the data is showing. The little red dots are still being cataloged in growing numbers. More interstellar objects are expected to be detected as survey telescopes improve, and each one will likely get the same careful spectroscopic treatment Webb gave 3i Atlas. More hidden planets are almost certainly waiting inside other well-studied systems, waiting for someone to apply the same technique that revealed Beta Pictoris d. And astronomers are actively searching for more examples of non-rotating galaxies to figure out whether the one they found is a rare oddity or the first known member of a previously unrecognized category. There's something worth appreciating in how quietly all of this happened. No dramatic announcement, no single unveiling event captured the full scope of what's been found this year. Instead, it arrived the way most real scientific progress does, in a steady stream of papers, press releases, and quiet updates to a growing body of knowledge, each one representing months or years of careful observation, data analysis, and peer review before ever reaching public attention. That steady, methodical process is easy to overlook in a media landscape that rewards single dramatic moments, but it's exactly that patient accumulation of evidence that gives these discoveries their weight. A hidden planet confirmed through multiple spectral lines. A black hole's activity verified against alternative explanations before being announced with confidence. A comet's ancient origin pieced together from careful chemical analysis rather than guesswork. This is what real discovery looks like, less like a lightning bolt and more like a fog slowly clearing to reveal a landscape nobody had fully mapped before. It's also worth remembering just how much competition there was to get this telescope built in the first place, and how many years of delays, budget overruns, and skepticism it survived before ever reaching orbit. For a long stretch, it looked entirely possible that the project might be canceled outright, its cost ballooning far beyond original estimates, its timeline slipping by years at a time. The fact that it eventually launched, successfully unfolded its enormous mirror and sunshield through a sequence of hundreds of precisely choreographed mechanical steps that all had to work correctly on the very first attempt and then settled into its distant orbit a million miles from Earth, is itself a minor miracle of engineering. Every discovery described here, every hidden planet, every ancient black hole, every ghost of a star hiding behind a wall of dust, exists only because that fragile, complicated, impossibly expensive machine worked exactly as designed, far from any possibility of a repair mission, entirely dependent on getting everything right the first time. It's easy to take a finding like Beta Pictoris d and treat it as simply the next headline in a long series of space news. It's harder but more accurate to see it as the payoff of one of the most ambitious engineering gambles in the history of science finally fully paying off. So when you hear that the James Webb Space Telescope just detected the unimaginable, understand that it's not a single moment, not one discovery, but a pattern repeating itself across every corner of the universe this instrument has turned its attention toward. A planet hiding in a system studied for 30 years. A black hole growing at a pace that shouldn't be possible, glimpsed just 570 million years after everything began. A comet older than our own solar system, drifting silently through the dark for who knows how long before crossing our path. Weather patterns on worlds so extreme they make anything on Earth look calm by comparison. A galaxy that appears to break one of the most fundamental rules galaxies are supposed to follow. Each of these findings on its own would be worth remembering. Together, they represent something bigger, a telescope operating exactly as its designers hoped it might, not just confirming what scientists already suspected about the universe, but continually finding the things nobody thought to look for, the details hiding in the gaps of our understanding, waiting for an instrument sensitive enough, precise enough, and patient enough to finally bring them into view. And if the last 4 years are any indication of what's still to come, the universe still has a great deal left to reveal, hidden in plain sight, waiting for the next observation to pull it into the light.